Hey students, I thought I'd make you a video here and go through these 5 questions on the exam. Hopefully you'll take some time to look at these and be kind of curious and kind of do 2 steps here. The first one is self-grade and kind of look over it. You'll get an idea of what you did wrong and what you did right, and hopefully more right than wrong. And also, you'll learn from any of those mistakes, and so that you won't make them again. And that's kind of the best part here. So let me go ahead and begin here with number 1. Number 1 says that we have 500 grams of aluminum at 230 degrees, and then is brought into thermal contact with 700 grams of lead at 22 degrees and is insulated from everything else. And then A, what will be the final temperature? And so we did a number of problems like this. We kind of wrote it this way, that the sum of the Q's would be 0 because one object, in this case the aluminum because it's the hottest one, is going to lose energy and the other one's going to gain it, which would be the lead. So if I kind of drew a picture here, I would have aluminum, and maybe I put it in contact with some lead, and energy's gonna flow. And since it comes out of the aluminum, that's going to be a negative number, and it goes into the lead, and they have to be equal in magnitude because of conservation of energy. And since these are solids, we'll write them as MC delta T. So I'll have an MC delta T for each object. And now I'll put in my numbers here. Let's see. So I lost the problem here. Where to go? Aluminum is 500 grams. And now we need to know the specific heats of aluminum. And I'll just flip over to chapter 20 for that. 0.9 joules per gram for each degree Celsius it changes. And then the change in temperature of the aluminum would be final minus its initial, which is 230. And then, of course, notice it's going to cool down, so that's why this is going to come out to be a negative number. Also, keep in mind that anytime you have a change in temperature, you can use Celsius or Kelvin. And so you'll see throughout this exam that, we've got to be careful whether we're using Celsius or Kelvin, but basically all of our equations are in Kelvin, except though change in temperature on Kelvin is the same as temperature on Celsius. So we can get away with using Celsius if it is a change in temperature, not just the temperature. And as you'll see throughout the exam, some of them will be delta T, so I'll use Celsius or Kelvin, whatever I feel like it. And then the other ones are on Kelvin, and so or just temperature, and so I must use Kelvin. All right, now let's do the lead. The lead was, where'd it go here? I think it was 700. Yeah, there it is, 700. So we got 700 grams of lead. And again, looking at chapter 20, this is what, a 0.128 joules for each gram, each degree Celsius. And so then if I go final minus its initial, which is 22, and then set the whole thing, excuse me, equal to 0. All right, well, grabbing a calculator, maybe I'll do the 500 times the 0.9. That's 450, and I'll have final temperature minus 230 for that one. And then here I'll do 700 times 0.128, and that'll be 89.6. And again, final minus 22 equals 0. But now I suppose there's a lot of different ways to do the mathematics, but maybe I think this might be the easier way. Divide everything by 89.6. So I can just take and copy that 450 and divide it by the 89.6, and then this would be 5.02 final temperature minus 230. And the advantage of doing this is now what's going to make my distributive property really easy here for this second one. and even made my numbers not so big here. So for both reasons, I think the division before the distributive, it might be a nicer way to do it. So then if I do the distributive property, this would be a 502 and this would be a 1, and adding together is 6.02 times the final temperature. And then on the other side is just simply this 22, and maybe the more interesting one would be that 502 times the 230, making 1155, and I'll just go 0.1. And so this gives me a final temperature. So I'll add the 22. Adding the 22 and dividing it by the 6.02 gives me 195.5 degrees Celsius. Had I done it in Kelvin, I guess I would have gotten 468.5 Kelvin. And so either one of those are equally valid. I won't stress over one or the other. But again, just remember our unspoken rule that, if somebody gives you units of degrees Celsius and asks you for a temperature, then it's kind of implied that you'll give it back in the same units. Just like if they give you pressure in pascals, you should give the answer in pascals. Or if they give you volume in liters or cubic centimeters or cubic meters, give it back in the units that were given. Kind of a unspoken but not required rule on my part. But I'll go with the Celsius for this one since it was given in Celsius. Okay, so then the second part of this is what is the total change of entropy. So maybe I should have put a little part A and now part B. And the change in entropy was this integral about heat. And it looks like there would be two objects, but both of them, then we would calculate their heat as we did here with an mc dt for a microscopic amount of heat, just changing this Q into a kind of a dQ over T. And so we're going to get an MC that pulls out in front, and then the integral of dt over T is the natural log of T, and if you evaluate it from some initial to some final, you will get this equation for the change of entropy for anything that has this kind of structure. Now, there are other structures. In fact, kind of a common mistake is, maybe I'll put it over here, mistake, is for students to treat the temperature as a constant, pull it out in front, and you just simply get a Q over a T. And that wouldn't work for this case because we don't have a constant temperature. Sometimes we do, but not in this case. So this is the two we would want. So I would have like a change in entropy of the aluminum and also a change of entropy of the lead. And since the aluminum is cooling down, the molecules are moving slower, this should be a negative and this should be a positive. And so the total will be just to add these two together. So for the aluminum, I'm going to take this equation right here, this 500 grams, the specific heat, which is 0.9 joules per gram, and I could put per change in degrees Celsius or change Kelvin. I'm going to switch over to Kelvin because that's kind of the units that we're used to seeing for entropy is joules per Kelvin, but joules per change in Celsius is just as equal. But we've been doing Kelvin, so I'll switch it now. And then notice, by the way, then the second one is the temperature, not the change in temperature. So I must do it in Kelvin, and so I'm going to take the 195.5 for the final temperature and add 273. And then likewise, the beginning temperature of the aluminum is 230, and I'll add to that 273. And I'll calculate that out in just a second, but let me write out the lead. The lead is 700 grams with a smaller specific heat of 0.28, I believe, yeah. And same logic, grams per Kelvin, so this will be joules. And the natural log of its final temperature, which again is that 295.5 plus 273 in Kelvin. And its initial then is 22, right? Yeah, 22 plus 273. And by the way, notice the units here in the quotient will cancel off. By the way, they'd cancel off if I use degrees Celsius also, but my formula is not right. My numbers aren't right. And just because my units work out doesn't mean my numbers are. And they won't work out right for Celsius. So don't put Celsius here. Like I said, we can get away with it anytime there's a delta T, but this is not a delta T. This is from initial to a final temperature. Okay, so grabbing a calculator here, I'll do this first one. Maybe I'll do this inside here. 195.5 added to 273, that would be the numerator. And if I divide it by 230 plus 273, that's the ratio. So then if I do the natural log of that, hopefully I get a negative number. Good. Like I said, this is the aluminum cooling down, should be a negative number. So there's the harder natural log. So then let's multiply it by 0.9 and let's multiply it by 500. So it looks like a negative 31 point, and I'll go 97 for the moment, and then joules per Kelvin. And then we can kind of do the same logic here, the 295.5. added to the 273 divided by the 20, well, I was going to say I could do that one in my head, but we'll just do the quotient, then we'll do the natural log of that answer. And again, positive, good, because again, it's warming up. And then times 0.128, and then times 700. And so this is a plus 41.44. And so now if we put the two together, let's see, where was it? Up here. There it is. And we add them, we get a positive and a negative with a difference of 9.47 joules per Kelvin for the total change of entropy. Yay! All right, so there's number one. 2 parts, and obviously part B, I think a little harder, especially since it was the last thing we did, and the concept of entropy is the hardest, although the concept wasn't really involved here as much as just a calculation. But it is an integral, and like I said, very tempting to do this, or very tempting to be careless and do things in Celsius. Just remember, it's always Kelvin, except when we can justify also using Celsius. All right, so maybe I'll call this page 1. All right, and on to page 2 and problem number 2. Okay, so here we have 1,600 joules of heat is added to 2.55 moles of an unknown. Okay, so keep in mind we don't know what type of gas this is. And it's in a fixed volume container. Its temperature then increases from 50 to 80 Celsius. Okay, keep in mind that Celsius also. Then the gas is now compressed. Okay, so no longer a fixed volume. Quickly, to half of its volume. And then a little hint here. The first sentence will give you CV. Once you have CV, you can get CP. Once you have those two, you can get gamma. And we're going to need it here. Because the other hint is compressed quickly means adiabatic. And so the first part, A, says, what is the final temperature? And I would encourage you to start off this problem with a PV diagram. I've been emphasizing that they can really help your thoughts a lot. So let me call this the starting point. I'll call it A. And that first sentence said we're going to add a Q to it. We're going to add heat, right? Q. 1600 heat is added to, and it gives us the number of moles, an unknown gas, fixed volume. So fixed volume is isovolumetric. So I'll call that A to B. Because then it is compressed adiabatically to half its volume. So if we call this V initial, on my graph, V initial divided by 2 would be somewhere about there. And so remember that adiabatic is that steep sloping curve. Let me call that point C. And so there's my PV diagram. And like I said, I think it would help to look kind of closely at this. Now, following the hint, we know the first part is adding heat energy at constant volume. So I'll use the CV. And in fact, you can then even see numerically that this is giving all the information except for CV, and that's why I can get CV. Now, I paused for a moment because my delta T here gets me back to what I said before. Do I want to do this in Celsius or in Kelvin? Either way is the same, and so why don't I just do the Celsius, since they give me a final of 80 and an initial of 50. And so the change is 30. And that will allow me to find CV. So I'm going to take the 1600 and divide it by 2.55, and then also divide that by 30, and it looks like it gives me about a 20.9. Which, I don't know if this is necessary, but if you write that in terms of R's, that's like 2.5 R's. You can see that if you divide it by 8.31, you get your 2.5. That's 5/2 R. And so there's 5 degrees of freedom with this gas, and so maybe it's some kind of diatomic, like maybe nitrogen or something. But what it is doesn't really matter. We just need things like CV, CP, and gamma. And once we have one of those, we have the rest. And so the way to get CP is you add an R. So let me just copy down CV and add an R. And so CP is 29.2. And then gamma is that ratio. So if I take that number and divide it by the 20.2, I get about a 1.40. And not a surprise, because once we saw this 5/2R, this should be 7/2R, and this ratio come out to be the 1.4 that you've seen a lot in the homework when we were working with nitrogen, or oxygen, or chlorine, or fluorine, or any of the diatomics. Actually, chlorine, something weird goes on with chlorine. Chlorine doesn't fit this model really well, even though it is diatomic. Okay, but along those lines, I am not quite there yet. In fact, I probably should have started here with why I need gamma, although the hint kind of helped me out. So I guess I was just following the hint, which allowed me to find CV, CP, and gamma. But if I didn't have the hint here on the test, I probably would have started this process something by saying, okay, this right here is adiabatic. And I actually know the temperature here. The temperature here, they say, is 80 degrees Celsius. And the temperature here is 50 degrees Celsius. And let me just add the 273 to it. I guess I don't need a calculator for that simple one. Same thing here, I guess. This is what, 323 also. But a lot of these calculations may or may not need Kelvin. And so, as we said on the other problems we've done, delta T is fine in Celsius or Kelvin. But since this is adiabatic, I'm going to put something like PV to a gamma, so at B, has to equal PCVC gamma. And then if you remember, we can replace the pressure with nRT over V. And then this would each be at point B. And this would be a C, so nR, temperature at C over volume at C, gamma, or volume at C to a gamma. The N and the R cancel, and you end up with something that would have been fine to start here. And I have a feeling a lot of you will start with this equation instead of the one we derived in class, because we've used that a number of times and you don't need to go through these steps during the exam. But like I said, without a hint, I probably would have wrote this down first and then realized that I know the temperature at B. They give me not the volumes at B and C, but some kind of ratio, so I won't bother to find those, although it looks like I have enough information that I actually could find those volumes. But the gamma was the big thing. And so if I'd started this problem realizing I need gamma, I would then backtrack to this. But with the hint, I got gamma right away. And then again, notice these are temperatures. So these got to be in Kelvin. These come from the ideal gas law. They're not delta T's. So I'm going to put in my temperature here of 353 Kelvin. And maybe I will just leave temperature at C by itself, because that's what I'd like to find. That is the question at hand. What is the final temperature? So we know it went from 50 to 80 Celsius, or maybe I should say 323 Kelvin to 353 Kelvin. And then when it gets compressed, it's really going to go up in temperature. And that's what I want to know, its final temperature at C. Okay. What's nice then is I can write this as volume at B over volume at C, gamma minus 1. And so let me just save paper here and write the 353. But you can see that the B is the initial, and then I'm going to divide it by volume at C, which is half that much. And so that just comes out to be a factor of 2. I guess we could write it as V initial over V initial divided by 2, which is 2. And then the gamma is the 1.4, so if I subtract 1 from it, it's 0.4. So grabbing my calculator, I can go 2 raised to a power of 0.4. Okay, so 1.3 times the original temperature of the 353. And so it looks like 4, I'll call it 66 Kelvin, would be the temperature, at least in Kelvin. And since they gave me in Celsius, maybe I should, again, subtract the 273. So I'm finishing the problem with about a 193 degrees Celsius. That would be probably but either one. But Celsius might be the better answer here. Again, kind of with our unspoken rule. They give you in Celsius, so give an answer in Celsius when they ask for temperatures. All right, so there's A, and then B says how much work is done on the gas. Now, fortunately, or maybe even unfortunately, probably even more, but I can think of 3 different ways of getting there right away. I think studying the PV diagram is nice, because if you kind of make a little chart here and say, okay, here is my energies, delta E, here's my Q's, and here's my W's. And so maybe I'll have the A to B process and then the B to C process. Adding these then is the total. And so if I can find, say, the 2 works, I'll call that the front door method. I can just add them together. And A to B you gotta love, because the work is 0. It would be the area under the curve, or as we said, since work is force times distance, something that is isovolumetric has no distance, it does no work, so that's 0. And the other one is adiabatic from B to C, and so I'll put a 0 there. Which, again, kind of the front door approach says, okay, I've got the work from A to B, that was easy. So now if I just find the work from B to C and add them together, which since 1's 0, it would be real simple. And we've done a couple of these integrals again. And so if you've kind of memorized the formula, great. They were a harder integral, so I tell you what, I'm going to do kind of a backdoor approach, because I do know that these 2 added up give me my delta E, and delta E is one of the easier ones to get. It is always just NCV delta T. Even though it's not an isovolumetric process, we can use it for the delta E. We can't use it for the Q or the W, but we can use it for the delta E. That was kind of our state function argument. And I know this change in temperature. You know, I know, looking at B to C back here, it started at 353 and it warmed up to 466. So I think I should do this calculation right here. I'll need the number of moles. So coming back to this problem, number of moles, 255. So 255. And CV is what we did earlier, 20.9, right here. And the final of 466, if I do Kelvin, and 353 if I do Kelvin, which, by the way, I don't have to, because it's a delta T, so I could do Celsius. So this could just as well have been 193 minus 80, same number. But that'll give me that number, which is that number, which is the answer we're looking for. And so 2.55 times 20.9 times 466 minus 353. Hit enter, and we're looking at about a 6,000-ish. I'll go 6,022 joules. And if I put that there, then these two have to add up. This has to be 6,022. And if I add these up, it's 6,022 joules. So there is my work being done, and the answer to B. Now, maybe at the risk of taking too much time away from the other problems, if I was doing a front door approach, I might just calculate the work with an adiabatic. And we actually did that. I think it was 1 over gamma minus 1, and then it was final pressure times final volume minus initial pressure times initial volume. And I'm not 100% sure on that one. Like I said in class, I don't always and seldom do that one because it's so easy to do this one, and these two just add up to here. But I know it was in the book, and I know you did a homework on it, so it wouldn't surprise me if some of you did it that way. In fact, I need to probably just take a moment to convince myself that I'm remembering correctly on this one. And I know during an adiabatic process, the pressure times volume to a gamma is equal to some constant. I'll call it K. So I could replace pressure with K over volume to a gamma, which I'll take out the K and write it as minus gamma in the exponent. And then that way, when I integrate it, it becomes gamma plus 1 over the same exponent, so minus gamma plus 1 evaluated from initial to final. If I take this K and take that negative and distribute it, it would be gamma minus 1. So that's looking good. And then this, of course, would then be the final volume minus gamma plus 1 minus the initial minus gamma plus 1. Okay, now looking a little closer at this K, remember this is true for initial as well as final. The reason I say that, because if I write this as 1 over gamma minus 1, that looks a lot like this. And then here I can write this as a K times final volume minus gamma plus 1. And then minus a K initial volume minus gamma plus 1. But I like where this is headed, because if I write K in terms of its final, I will get then a pressure final and then times the volume final to a gamma, but I'm also multiplied by this final to a gamma negative 1. And so those would cancel, and then you're just left with this final volume to this 1 power right there. Nice. Yeah, and so we're there now, because watch the same thing for the K. If I use initial, this would be initial pressure. And then when I multiply it by the initial volume to a gamma, and then this has initial gamma to the initial volume to a negative gamma, they'd cancel off, and I get left with just initial raised to a power of 1. So, like I said, during an exam, you probably wouldn't want to go through all this math, but also, since you have your notes there in front of you, and we already did this, you might just grab that one. So maybe that would have been an easier process here. Not sure, but that one, kind of the backdoor approach, came to my mind. But if you put those in, this is what you would get. And, by the way, kind of the third idea that popped in my head is you could then use the ideal gas law, because pressure times volume is NR times final temperature. So each of these would have an N and an R, and this would actually reduce to something really nice, NR delta T. In fact, maybe I should just write it as NR delta T over gamma minus 1. And given that we were already at this spot and getting the temperatures, this would have been actually an awesome way to get there. But getting to this equation might be a bit cumbersome. So, and I don't recall us doing this one on the homework or anything. So I don't think you're going to have direct access to this one. But I could be wrong there. But direct access to this one would be also a very quick way to do it. It would be all front door and easy. So that would probably be even a better way than I did it. Anyways, those are the three things that popped into my head. And then this is the way I always go. But this one, just like I said, I have a hard time remembering that one, just because I just don't bother to use it, because I've got the backdoor approach. Although sometimes maybe the information they give you is this, and That's the way to go. But this is really nice too. All right. Anyways, that's kind of just a freebie. Take that for what it's worth here. But you got a little freebie there. All right. Let's go on to page 3, and then I'll call it, in problem number 3. And problem number 3 looks a little long. In fact, I think it probably is the longest of the 5 problems here. It says you have 1.42 moles of helium. There we go, monoatomic. Keep that in mind. Gas at a temperature of 25 and 1 atmosphere. So watch our units here. That's not kelvins and that's not pascals. And it looks like they're going to be asking me about energy. 1 atmosphere of pressure, and it is warmed. So its pressure is proportional to the square of the volume. Okay, so this is the equation, and so it kind of fits in this PV diagram. And K is some constant that can be found from the initial conditions. And again, there is no name for this. The PV diagram is shown at the right. The gas is warmed until its pressure is doubled. Okay, so this is the initial pressure. We're going to go up here to twice the initial pressure. And so, by the way, if this is initial volume, you can see in here that then this must go to the square root of 2 times the initial volume, so that when you square it, you will get a factor of 2. I think that's going to come in handy. All right, PV diagram as shown on the right. The gas is warmed until the pressure is doubled. What are, okay, and then we're going to try to find the new pressure. And so this pressure up here, the new volume, this volume here. Volume, the new temperature, energy added by heat, energy added by work, and the change in internal. So all 6 of these options is our planned attack here. Okay. There's even a hint. You can use the PV diagram to find the K. Okay. And so you can see here we were given pressure, we're given the number of moles, we're given the temperature. And so maybe the first thing I would do here in number 3 is to say that the volume is nRT over P. So the number of moles is 1.42. R is 8.31. The temperature is the 273 plus 25 degrees Celsius. So let me say it again. This formula has temperature, not change in temperature. So I don't want to be in Celsius. Okay. So this is going to be a 298 on the Kelvin scale. And if I use pressure in pascals, so I'll change the 1 atmosphere to pascals, which I need to because I used the 8.31, which has then volume in cubic meters and pressure in Pascal and moles and temperature in Kelvin. This then will give me my initial volume because I'm using initial pressure and initial temperature. Okay, so following the hint, 1.42 times 8.31 times 298 divided by 101,300. And it looks like I'm at 0.0347 cubic meters for my volume. I guess if you did it in liters, it would be 34.7 liters, but I would recommend not doing liters, doing cubic meters. Which, by the way, the second part of that hint then says you can find this constant value. You can just take pressure and divide it by volume squared. And so if we take initial pressure, 101,300, and divide it also by the square of the initial volume, and of course, I guess if we put in our units, we would get pascals over meters to the 6th power. 101,300 divided by, and I'll just take the last answer, and square it. And it looks like I get an 8.4. Why don't I go 07 just to have an extra decimal, I guess. I was going to go to 1, but I'll go 7 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. Okay. And then, of course, the units are in pascals and meter to the 6th power. And then this will be a perfect option to get, I guess, the beginning answers. First of all, here when it says the pressure is doubled, I could just take my 1 atmosphere and then say, okay, well, this is 2 atmospheres. But I think I will do it as 202,600 pascals. So that's pretty simple. I argued, based on reading the mathematics here, that you could take your original volume and multiply it by the square roots of 2 and get 0.0491 cubic meters. But at the same time, we could just as easy use this equation now that we found the K value, and we could just take the final pressure, 202,600, and divide it by the K, which let me just go up here and grab the K and hit enter. And now get the volume by taking the square roots. I hope I get to the same thing. It's kind of a safety check. Yeah. And so 0.0491 would be my volume. And as we've talked about so many times, if you have any two of these, you can find the third. And so temperature is pressure times volume over nR. And so in my case, I got the pressure of 202,600. I've got a volume, which is that number right there, so I'll just copy it. I'll divide by n, 1.42, and I'll also divide by r, 8.31. And so we're looking at a temperature of about 843 Kelvin. And depending on how you want to look at this, I'll take either one. This is 570 degrees Celsius. And so maybe I'll put 570 degrees Celsius, and maybe even underneath it, 843 Kelvin. And again, I wouldn't make a big deal over the Celsius or Kelvin, but they gave it to me in Celsius. And actually, for that matter, they gave me pressure in atmospheres. So by that logic, I'd have to go back to 2 atmospheres. But atmospheres are just annoying when you're dealing with energy. So I'm not, even though it's kind of the unwritten rule here, I guess I'd call it an exception, because it's like, no, better with pascals. So I can get my energy in joules. This atmosphere doesn't do me any good. Okay, so then we get, I think, to maybe some of the harder calculations. You heard me say it back, I think, on problem number 2 here, that you want to look for which ones are zeros here. The work is 0 for isovolumetric. We don't have that. Q is for the adiabatic. We don't have that. And the isothermal here, and we don't have that. In fact, we have none of those. So we can't do the easy ones with the 0. But we can say this, and this is probably the key, and maybe even a harder part of the problem, is we can go NCV delta T. NCV delta T is true all the time, regardless of what kind of process it is, even though we discovered it during the isovolumetric process. But that was our argument about a state function, is it is independent of what process. It's path independent. So even though we found it during the isovolumetric process, that means we can use it for any other process, including some other process that wasn't named. And so this is it. And this is then what I'm going to do. I'm going to say, okay, so delta E is NCV delta T. So the number of moles is 1.42. CV, this is where the helium comes into play. It's monoatomic, so it has 3 degrees of freedom, so it's 3/2 R. And then the change in temperature, and since it's change in temperature, I can use Celsius or Kelvin. Why don't I do Celsius? Because I have this 570 degrees Celsius when it finishes at, and then it started at 25 degrees Celsius. All right. And so grabbing my calculator here, 1.42 times, and I'll just go 3/2 as 1.5, times R, 8.31, times this difference, 570 minus 25. And so I get 9,647 joules here. So 9,000, what did I say, 647 joules there. Now, here's where, maybe these are even harder. I can hit a roadblock. The Q is definitely path dependent. And I have equation for Q at constant volume. I also have a Q at constant pressure, but that's it. Well, unless you do adiabatic is 0. But I do not have any kind of special formula for this process. I've never done this process, maybe on the homework or anywhere else. So I don't really, and it depends on the path. So we don't have anything we can go directly look at. But remembering that these two add up to that one, the first law of thermodynamics, maybe I ought to set my sights on doing the work. And then from there, I would have these two, and I can get the Q. And since the work is minus the integral of P dV, this looks very promising. This is the area under that curve. Now, it's not a nice simple rectangle, so using geometry to get the area is not going to work, but I can actually do the integral. I know the relationship between pressure and volume, and that's what is required here. So this looks very promising. So I'll replace pressure with K times volume squared dV, and then that way, taking out the K, I'll have an integral of just volume squared, which makes volume cubed over 3. And I can now evaluate it from the initial volume to the final volume. And so this is going to be a minus K over 3. And then the final volume cubed minus the initial volume cubed. And so let me put all of that into my calculator. And maybe I'll do this first. So the final volume was at 0.0491, and let me cube it. And then let me subtract the initial volume, which was the 0.0347. And then let me cube that. And I'll just hit enter there and get that in parentheses here. Now I'll multiply it by a negative K, and the K was the 8.407 times 10 to the, what was it, 10 to the 7th here. Okay, good. And then all of that is also divided by 3. And so it looks like I get here a negative 2146 joules. And the negative is exciting because the gas did expand, and that means it lost energy due to its work. It's pushing on the environment, and that's what that negative would do. So that's good. And so if I put that in this little box, negative 2147, I can now finish this by saying delta E is equal to Q plus a W, or put another way, the Q I want would be the delta E minus the W, which is a negative number, so it's minus a negative. All right, so coming back here, I can put the 9647 and then minus a negative, so I'll just do plus 2147 means that the heat that was pumped into this is 11,794. So 11,794 joules. And I like all those numbers. I mean, like I said, I like the negative. And so this is that leaky bucket analogy. I said for the gas to do this, you've got to pump in lots of heat. So you're putting lots of heat energy into it, 11,000. And then while you're doing that, it loses some. The bucket leaks a little bit. And so your net gain is only 9,647. Even though you put 11,000 and change, but some came out. So there. Okay. Well, like I said, I thought that might be a long one. Okay, well, let's keep going here. Let's go to, I guess what I'll label here as page number 4. And looks like it's a little bit on efficiency here, but we got a small power plant makes electricity, and it burns a little natural gas, and then, of course, it uses that to make steam. The steam is warmed to 400 degrees C under high pressure. The expanding C turns a turbine and produces the electricity. The exiting steam is at 130. Okay, so it looks like here's where the work is being done. The high temperature and high pressure pushes, and as it pushes it, it loses its pressure. It does work and loses some energy. Which is why it's going to be a little colder. And I guess we don't want to get into 100, less than 100 C, turn into a liquid. It says here the power plant produces electricity at a rate of 25 megawatts. And the power plant has an efficiency of 32. It also then says natural gas releases 55.5 megajoules of heat for every kilogram burned. And so A says, how many kilograms per second of natural gas does the plant burn? So at what rate is it burning? Well, hopefully right away you recognize the idea of efficiency and maybe write down this. That the efficiency is defined as how much work do you get out compared to how much heat energy did you put in. And so the power plant is clearly getting 25. Oh, and by the way, that's watts. So that's work. So maybe before I do anything, I need to multiply the top by 1 over T and the bottom by 1 over T. So we have rates. And so the work per time, the rate, is equal to the heat per time, the rate. And that's ultimately what I'm going to need, because it needs kilograms per second. It needs a energy rate. Okay, so the efficiency is 32%. And the work coming out of it, the rate, is 25 megawatts. And so that means I can find the amount of heat per time, by taking the 25 and dividing it by the 0.32. So in other words, this plant must be looking at my units here. Yeah, megawatts. Okay, so this plant is burning enough natural gas that it needs to be giving off heat at 78.1 megawatts. Because when I multiply it by the 0.32, that's the percentage that gets turned into something useful. So that's our 25 megawatts. So we burn way more than double, which makes sense because if it was only double, that'd be 50%. So we got to be way more than double. Actually, a little more than triple, right? Because 33.3 would be triple. And so triple 25 is 75. Yeah, so we're just a hair over 75. And so this is how many watts of heat we are. And so now we need to think about what we mean by burning at a particular rate. And so you can kind of see it here in the units. The energy per time would, of course, just be the amount of mass per time multiplied by the energy per mass. Kind of our little chain rule here. So if I know the energy per mass, which is given, and then I multiply it by the mass per time, that's going to give me the energy per time. And so in this case, I know that one, and I know that one, and I'm asked for this one. So mass per time must equal the heat per time divided by the energy per mass. Okay, so this is the 78.8 megawatts. Let me write that as joules per second, okay, instead of a watt. Because then my energy per mass is given as 55.5 megajoules per kilogram. So the mega and the joules will cancel off. And this compound fraction will flip and multiply, and so I'll get kilograms per second. So the 78.1 divided by the 55.5 is going to give me 1.41 kilograms each second. And doesn't sound like a whole lot of gas. Volume-wise, depending on how much pressure it is, it can be quite a bit. Natural gas, the molecular weight's not heavy. So volume-wise, it could be a reasonable amount, especially if we go shooting it out at atmospheric pressure. So maybe it comes in pressurized, and then we shoot it out. But the real thing is, there's just a lot of energy in natural gas. So we can have a 25 megawatts, not exactly a big power plant. In fact, it even says a small power plant. All right, well, that's A. And then B, and along this same idea of efficiencies and the second law of thermal dynamics, I guess we had a second law here, or at least a chapter 22 in entropy, and this is also in our chapter 22. It says, what is the ideal efficiency? And so we learned that the Carnot cycle would be the most efficient. And so because of the second law of thermodynamics, we know we'll never be able to switch all 78.1 megawatts of heat energy into electricity. But at least as an engineer, we have a goal we should be shooting for, and that's the Carnot cycle. And so if we do something other than the Carnot cycle, we may get less efficiency. And this one doesn't say what the process is and how this gas is being burnt and expanded. But I have a feeling it's, being expanded quite quickly. And because it's quickly, it doesn't meet the isothermal process of the Carnot cycle. That's the unfortunate part of the Carnot cycle. So to get things to happen quickly, we sacrifice efficiency. But if we're willing to, or maybe if we're clever enough to get a new cycle, we can get, a Carnot cycle. Well, in either case, our gas, which is our steam really, it's our H2O, but remember it's way over boiling, so it's a gas. Our low temperature, and again, let's be careful here. It says it's 130 degrees Celsius, but don't forget to add 273 to turn it into a Kelvin. This is not a delta T, this is a T. And the high temperature is 400 Celsius. And again, we'll leave it in Kelvin. And so if I take the top, 130 plus 273, and divide it by the bottom, 400 plus 273, I get roughly 1/6. So then if I go 1 minus this last answer, this would be the Carnot efficiency. So we're looking at about 40.1% efficiency that, from a thermodynamics perspective, is achievable. And so now, from an engineering and materials perspective, can we get there? And so based on these temperatures, this would be our best efficiency. Of course, also you can see here that if you wanted to get more efficient, we can expand these ranges. Not easy to do. 400 is kind of the upper limit of our steam power plants. Our materials run into troubles. And then lower than this runs into troubles also, because now water is, well, definitely under 100, because now it's no longer a gas. But and then depend on what pressure also. But that just works against us. But here, that's getting a little too close. You will get water droplets to form, which will etch your dynamics of your gases flowing through these very precise turbine blades. Anyways, I know in the in-person class we had a little discussion about maybe to do multiple stages, go, 200 to, or 400 to 200. And then you can put your more exotic materials in there and you're way above it pitting, and then maybe a second stage where then you go 200 to 130 and it's not great quality and not expensive material, and so it pits, and you end up changing that out once a month, but the other one you keep in for a couple years maybe. So anyways, I digress here, but hopefully you did well on that one. All right, and then off to number 5, the last one here. Here we have a hollow cylinder, or excuse me, a sphere. It's a hollow aluminum sphere. It has an inner radius of 5 and outer radius of 6. Half of its volume is first filled with turpentine, and the other half is filled with, there it is, a diatomic gas, so keep that in mind, and a pressure of 1 atmosphere, so that's 101, 0.3 kilopascals. The whole system is warmed, so now we're going to warm it up. And due to thermal expansion, the nitrogen gas is compressed. Okay, so they kind of help me with my mental picture, because what I mentally see here is this chamber that's half filled with a liquid of turpentine. And then above it is nitrogen gas. And then when you warm it, two things are gonna happen. The turpentine expands, and so there's the natural gas, or not natural gas, the nitrogen gas getting compressed. However, the inner radius is getting bigger too. So that's going to give place for the turpentine to go. So maybe the turpentine won't quite expand too, or as much as I thought it would, into the nitrogen at first. In fact, possibly not at all. Maybe the level goes down, but I highly doubt that, because that means the aluminum would be expanding more than turpentine. And just knowing the numbers, that's not going to happen. Also, I guess the problem makes it very clear that the nitrogen is compressed. Okay. And now, the ultimate question here is, what is the pressure after warming? And for those of you who might know a little more chemistry, you would know that some of the turpentine would turn into a vapor, and you would have a more complicated gas mixture up here. And so we're allowed to ignore that. And also, if you looked too closely at turpentine, you're getting to its flash point, or still below its boiling point. I believe its boiling point was 154 degrees Celsius, and I kept it a little below that. So I wanted to warm it up quite a bit, but at the same time, keep it low. I mean, keep it below the boiling so that that issue doesn't come up. And in terms of flash point, it would, if I was doing this in an oxygen-rich environment, it would just flash burn on me right away, long before I got to 150. So got to be a little careful. But I think this would be okay. It wouldn't have to worry about it flashing, because I don't have any oxygen, and I don't think it would react with the nitrogen at that temperature. Okay, anyways, let's then do our calculation. And kind of the first thing that comes to my mind is, you know, P initial, V initial equals nRT initial. And for that matter, pressure final, volume final equals nR temperature final. As I focus on the nitrogen gas, I am looking for right there, what is the final pressure? And so if I kind of rearrange this to say initial pressure times initial volume over initial temperature, that would equal nR. But if I did that same kind of logic for the final, I would have final pressure, final volume over final temperature. And in fact, since my goal here is to find the final pressure, let me solve that one by itself by doing this. I'm going to take initial pressure, and I'm going to imagine putting the final temperature over there and above the initial one. And then also, I'm going to imagine taking the final volume and putting it over there, and then kind of switching the order. But I like it this way because here's what it tells me. It tells me that the final pressure is going to change from the initial because of two factors. One is the ratio of the temperatures, and one is the ratio of the volumes. And both of these should be greater than 1, because I'm going to warm it up so the temperature final is greater than initial. But also, the final volume is less than the initial. So this is greater than 1. So both of these are going to be reasons why the pressure is going to go up. So it goes up for two reasons: a smaller volume and a higher temperature. Then multiply by that original, and I will get the final. So it'll look something like this. The initial pressure, and if we left it in atmospheres, we would put a 1. But not a big fan, even though, like I said, that's kind of the unspoken rules. They gave it to me in atmospheres. So maybe I'll finish also in atmospheres. But I'll do both. I'll do atmospheres and pascals. But then I need these factors: the initial and final temperature. Now, fortunately, those are given. Now, we do want to be a little careful because they are given in Celsius, and this is not a delta T, these are a T. So I'm going to have the 273 plus 20 down here. That's 293. And the other one's the 150 plus 273, which is 423. So that's one factor. In fact, it might be kind of nice just to write that factor out. 423 divided by 293. All right, so it's going to go up by a factor of 1.444 just because the temperature goes up. But it's also going to go up by a small factor because its volume decreases. I doubt if it's much of a change in volume because it's just thermal expansion. But again, it is turpentine, which has the biggest expansion. So let's do some numbers here. Why don't I start with, I'll call the initial volume. Actually, maybe I'll do that on another piece of paper here. The initial volume of the aluminum chamber inside would be 4/3 pi r cubed. And so the whole chamber, I guess, would have this volume, 4/3 times pi times, and what's the inner radius? 5, but let me make sure I just focus on cubic meters. So I'm going to change the 5 to meters and then cubit. And so we're looking at about a 5.23, and there's not going to be much changes. So let me write this as a 60 times 10 to the minus 4 cubic meters to kind of get me going here. And so that's the initial volume of the aluminum. Now, the initial volume of the nitrogen would be half that, since it said it was half filled. So let me just divide it by 2 and go 2.6180 times 10 to the minus 4 cubic meters. And so there's my starting volumes. But there will be a change in volume. I'm sorry. I meant to say one more thing. So yes, this is the initial volume of the nitrogen, but it is also the initial volume of the turpentine. Okay. And I'll need both of those. In fact, the initial volume of the nitrogen is what this is. So this is going to be that 2.6180 times 10 to the minus 4. Okay, so now I just need to get that final volume. Okay, because I'm going to put here the change in volume of the turpentine would be beta times the initial volume of the turpentine times delta T. And so now I need to look up the beta, if you will, of turpentine. And looking on chapter 19, I see that it is 9 times 10 to the minus 9. So if I take that original volume of 2.6180 times 10 to the minus 4, and I multiply it by the change in temperature. And so remember, we're going, we were at 20, we're going up to 150. So that's a change of 130. And again, since it's a change in temperature, I can use Celsius or Kelvin. So the turpentine is going to grow a little bit. Let me take that volume. It's already in my calculator. Let me multiply it by 9 times 10 to the minus 4 and also by 130. And so the turpentine is going to grow by 3.0631 times 10 to the minus 5. But the space that is holding the turpentine is also going to grow. And so remember that holes grow as if the material was filled inside. So this would be aluminum. And so that inside chamber is going to grow. And so my aluminum, I'll have to do the beta for my aluminum, which, again, you won't find a beta listed. We never do for solids. It's kind of a waste of space. It's just three-dimensional, so it's 3 times our alpha. And then it's going to be the initial volume of the aluminum times the delta T. So this will be 3 times, and then here's where we need to go look up aluminum, which the linear expansion of aluminum is 24 times 10 to the minus 6. The initial volume of the aluminum is 5.2360 times 10 to the minus 4. And again, it's increasing by 130. In fact, now you can see the numbers. The beta here is, I mean, this is almost a 10. So this is like 10 to the minus 3. And this is more than 10. So this is like 10 to the minus 5, but kind of even double that. But this is almost 100 times bigger. I guess there's an extra factor of 1, 2, almost 3. So 33 times bigger. And then divide by 3, because then there's a factor of 3. So maybe 11 times bigger. That's a pretty rough number. Let me just call it 10 times bigger. So it wouldn't surprise me then that both are going to grow. The chamber where the turpentine is held is going to get bigger, but the turpentine itself is going to get bigger. But the turpentine itself is going to get about 10 times bigger. So there is going to be a growth to the turpentine, and that's going to compress then the nitrogen. And that's going to finish up our test when I finally get the final volume and see that the final volume is smaller than its initial. Okay, so putting my numbers in here, I can go 3 times 24 times 10 to the negative 6 times 5.2360. Oh, and this number is bigger also. So, you know, anyways, all these numbers are different out in front, but all these out in front come out to be less than that one. That one's just so much bigger than that one. 5.236 times 10 to the negative 4, and then finally times 130. So my growth in my aluminum here is 4.9009 times 10 to the minus 6. And so not much of a growth. In fact, you can begin to see, right, there's the factor of 10. So the turpentine is roughly 10 times, although these aren't quite the same numbers either. So, but somewhere in that neighborhood, it definitely is a bigger number, a whole digit bigger than that one. All right. Now, again, keep in mind what I want to know. What I want to know is the volume of the nitrogen after it warmed up. So what I'll need to do is take the volume of the chamber, which I'll call it the volume of the aluminum or the hole that is made by the aluminum, and subtract off the volume of the turpentine. And the hole is why I needed to do these two steps. I needed to take the initial volume of the aluminum hole and add to it the change in volume. So that's how big the aluminum is now. And then likewise, the turpentine, I need to take its original volume, 2.6180 times 10 to the minus 4, and then add to it how much the turpentine grew, or expanded might be a better word. And that leftover space is where the nitrogen is fitting into all this. Okay, so 5.2360 times 10 to the negative 4, adding to 4.9009 times 10 to the negative 6. And subtract off this whole quantity of 2.6180 times 10 to the negative 4, added to it 3.0631 times 10 to the negative 5. And so after all that work, I think the space left over for the nitrogen and is not as much as it started with, and it's compressed a little bit, right? So remember, we started with the nitrogen of 2.6, and now we are down to 2.3. And so here I'm going to put 2.3607 times 10 to the minus 4. And again, maybe just out of a fun curiosity, how much is this factor? The fact that the volume is smaller. And so this will increase the pressure by roughly 10.9%, whereas the temperature change is increasing it by about a 44.4%. So it's going to go up by both factors. And let me do the two factors together. 1.444 times 1.109. And together, this is 1.60 is the total increase. And by the way, that would then be the pressure if I wanted to know it in atmospheres, because this P would be in 1 atmosphere. But I'd like to finish this problem by then multiplying it by 101,300 and come up with 162,221 pascals, about a 1.6 atmospheres. And that was actually a little more than I thought. I guess it started pretty straightforward with the ideal gas law and the two factors, but then doing the thermal expansion, which involved more complicated than I kind of first thought it might, where it has, because I got to think about the aluminum and then the turpentine, and then it's squeezing it out, and the difference between those is what's left for the nitrogen. So there's quite a bit here, and I hope you did well on that. And I just noticed we don't need the 6 centimeters, the outer radius, for any reason. And that makes sense. Everything's going on inside, so that's just wasted or unneeded information. All right. Well, I probably talked too long. Hopefully you self-graded and corrected any of your mistakes, and you're that much better for going through the video. Take care.